Alright, hello everyone to another episode of Dan Does Data. We are still tonight looking at the self-driving car models, and I didn't have a specific topic in mind tonight. You might recall last week I worked on the transfer learning, and over the weekend I worked on a lot of different things. I just sort of want to take this episode to review some of the things we've done and see what might be left to work on as far as the model, and there might just be more practical concerns to work on the self-driving car itself, that maybe it's time to put the model aside for now and work on getting a good mechanical car that responds properly to commands. First, let's just go into this transfer learning. I mentioned last time I wanted to use SqueezeNet because it contains very few parameters. So I was hoping that would mean that it would work pretty well while still being very small and not consume all my memory. Always a concern. And so I found a Keras implementation of that. That worked reasonably well. I was able to actually implement SqueezeNet, do all that stuff. I tried both the full SqueezeNet, essentially, stopping after all the convolutions, and then switching to my own dense network. And then I also tried a mini SqueezeNet, where you stop after just a few layers of convolutions, hoping that you're just finding more intermediate level features rather than there's a dog's head in this corner or a cat's tail over here, something like that. And I believe last time I had it sort of working in the sense that it did something. This weekend I had the chance to actually load it in a little bit more. Unfortunately, it was not giving me the kind of results that I wanted, and it still took a long time to compute. I was a little frustrated with that. It may be that the architecture of SqueezeNet is not good for this application, and maybe that even the 20,000 data points I had or so was not enough, even with this transfer learning. That's what I was really hoping to get around. So maybe, as other people had suggested to me, the transfer learning that was not going to be a good success. I thought, all right, well, what else can I do? What else have other people done? I recalled that NVIDIA had been working on a self-driving car model, and I was curious what they ended up doing. And I also wanted to go back to the DeepDrive data set that I had started with. I was like, all right, well, maybe I can just get some more data. And I was reading the site, and maybe this was new, or maybe I just didn't see it before, but Craig had posted his model of what he actually did to get the car to drive, and he had a pretty good model. And what he did was sort of use transfer learning with AlexNet. I don't know if he started with the weights of AlexNet. AlexNet is a popular, well-known, pretty successful image recognition model using lots of convolutional layers and a couple other things I'm not going to get into. I believe he might have just used that shape and trained his network appropriately. And of course, at the output, instead of outputting, let's see where we get down here. Instead of outputting the 1,000 classes or whatever that you need to try to classify for images, he's outputting 6 real numbers. There's like the yaw, the pitch, the roll, the steering, the gas, and the direction, or something like that. I may be mixing up one of those. And so he says, yes, the final output is a fully connected linear layer. So it's kind of the same thing that I'm doing. I'm just trying to get the steering. You might notice, however, his model does a pretty decent job. Let's just jump down there. Yeah, this road probably looks familiar. This is his model trying to drive, I believe. Well, that's a different view of the model driving. Alright, well that's pretty silly. Yeah, so it's doing not so bad. And he's got lots of cool outputs over here. Craig has a very good visualization. So I thought that was pretty neat. Alright, well maybe I can do that. So I asked Craig about where I can get the weights in a good format. He had very graciously released them in a TensorFlow sort of NumPy binary format, which I was able to read in. Where do I have this? Let me go over there. I did not open that file. DeepDrive.py, there we go. Which I was able to read in those weights. Where did I do this? This is some data. What? This is not the same file I thought it was. DeepDrive / slash. Nope. There we go. So let me just walk you through this real quick. And if this is very tedious, that's okay. This is just sort of video log. Question from the audience: did we figure out how to freeze the layers? I saw some stuff on Keras on how to do that, but not a good way. And Rick is here in the chat room. He made it back from Oculus conference. He caught a cold. Oh no, Rick. Hope you get better. If you went to the Oculus conference, do we have an Oculus kit? Can our car drive with virtual reality? None of that makes sense. I'm just using buzzwords right now. Don't worry. Anyway, we have this model which I was trying to emulate AlexNet in Keras. And this is non-trivial because AlexNet sort of takes, for a lot of the convolutional layers, it splits them into two pieces. And so like half the kernels are over here and half the kernels are over there. And they get rejoined in a particular way. And so I was trying to figure out the right way to do that. And I was fighting with it for a little while, and then I said, all right, maybe I should just spend some time and find out if someone else has already done this. I thought maybe someone would have already implemented AlexNet in Keras. And in fact, someone has done that. There was a company or a person called Heuritek, I assume for heuristic. So they had already implemented AlexNet using this funky, that handled those funky things. They basically had to merge them back together and all this. So you can get AlexNet on Keras if you go to the Heuritek GitHub page. Essentially, you do this, and just on the last layer is what Craig changed for DeepDrive. You change the output. You say, okay, that's great. And we have the weights, and I want to stick the weights into Keras. And it's like Keras wants them as a list of NumPy arrays, but I had them as a sort of single large NumPy array in a sense. And the shapes of things were slightly different because of how layers get grouped because of this convolutional splitting or grouping. This is like a feature of the Cafe software that Craig used, but not of Keras and some other ones. Thankfully, I was able to like just look at all the shapes and sort out how to do that. Let's see if we can do that actually. Let's run some of this model, shall we? 0, yeah, there we go. That will probably be the most interesting thing to do, and then you can see how we can actually read all this in. Well, that's not actually what I want. Come down here. Here we go. This is the model we want. Oh, something wasn't happy. Something was not happy. Why? Oh, because I'm not in the right directory. There we go. Big money. Look at that. So yeah, you got to do the split tensor, and then you merge them back together. All this silliness. And the model's a little big, I think. You got this layer of couple layers of 4096 things. Another question from the audience: what GUI are you using? I'm not using a GUI. I'm using Tmux. Tmux for great victory. So it's just Tmux. I got Vim on the right, and I got IPython on the left. It's pure, just sort of like pure coding. Nothing gets in the way. And there's like a little bit of black down at the bottom, which may or may not even show up on YouTube. I wish I could get rid of that. If I fiddle around with the font size, I could sort of get rid of it. But that is to me an imposition. It's a waste of space in my interface. But you notice I full screen the interface here. I cannot stand to have wasted screen real estate. That's for a long time why I used Arch Linux, because it was very easy to control the real estate. But it's also now easy to do that in Ubuntu. So you look at WM, which is sort of like what the weights are for this model, just randomly initialized. And you say, well, what's the first shape look like? Are you able to download the entire training data set? So for DeepDrive, I chose not to download the entire data set because that's 80 gigabytes, and that's going to take my computer way too long to try to process. I'll essentially be waiting do one pass of the training data is going to take way much longer than I want to do in a video, and much longer than I personally want to wait for. I gotta get the W. So this is what the actual weights want to be in Keras for the AlexNet. If you want to do transfer learning, you'll have to do something like this. But I had weights that looked like, oh shoot, did I not load them in here? Now I feel silly. Did not load in the actual weights. Oh, ridiculous, ridiculous. Now I have to go in here, see where they live. Read weights. Oh, what do you know? Tab new, DeepDrive, read weights. Hey, what do you know? So there were two different weight files that Craig had, but I think they were identical. Another question from the audience, what's my GPU configuration? Let me just show you NVIDIA SMI. And you will see that I'm using a GeForce GT 620, which is like 5 years old. I do have 2 gigs of video memory, which that to me is always a big limiting factor. But another big problem is often just how many CUDA cores you have. And does your CUDA card, or does your GPU support common machine learning libraries? So like Theano works on my card, but not TensorFlow. So that's why I don't use TensorFlow. I probably would if it did work. So let's just load in those keys. I think that they were identical. I checked, and they're stored in NumPy, was it, file format? Yeah, but it was like this weird NumPy format where you had to like ask for the item, and then it's sort of like a dictionary. I wasn't familiar with it. I guess it is a NumPy with named things, but I found it arcane to deal with it. So I did that, and I grabbed, okay, just give me the weights, give me the biases. So now I have this W array of all my weights not from AlexNet, from Craig's trained DeepDrive model, and all the biases. And that is what you want to compare to the actual DeepDrive model. And so what you do is you say, all right, well, what's W0.shape? And they're like, all right, and what shape does it need to be? And that's this WM. And so you'll see, I just need to move these convolutional size window axes over here. And that's exactly what we've done here. The transpose sort of reorders the axes. And then I just need to do the bias. Ooh, that's not what I wanted. I need to do the bias vector is all. And you can verify that by looking at WM1.shape and B1.shape. B0.shape. Right, because it's the first set of biases. How can you check if your GPU works with TensorFlow or Theano? So you can try looking on the TensorFlow.org website if yours is supported. But the only way you can really check if it works is to try to run both. As a question of does it run better? That probably depends on what you're doing explicitly. I would just use whatever most people around you are using, because it's just going to be easier to collaborate at that point. And the syntaxes are very similar, I've found. So pick one, use it, you're going to be fine. I've heard that Theano can be a little bit easier to support, but I imagine with the popularity of TensorFlow, that's changing. Okay. Given these other layers, you have to deal with these funky convolutional layers. So the next layer here is one of these split guys, and AlexNet nominally has 96 kernels, but you note half of them are only listed here, 48. But in our proper weights, we have 48. Did I do this wrong? Am I crazy? Oh, no, sorry. 48 does not. I am not crazy. No. That first layer, it's this is the number of kernels. That's the number of channels. There's 48 channels. Yes. That part makes sense. This is the 128 versus the 256 is the problem. So what you need to do is say, all right, well, the first half of these are going in the first half. Like, I tried looking up, is there a specific place? Like, which one? Is it the evens and the odds? And I think it's just the first half and the second half. Someone please correct me if I'm wrong, because that may change whether I really want to use this. Another question from the audience: how do you check which is better, TensorFlow or Theano for AlexNet? That I don't know. I haven't tried running it both ways. I haven't personally trained an AlexNet type model. So that would be good for someone to try out. Do a benchmark in Theano, do a benchmark in TensorFlow, see what happens. I'd be interested to see the results. Anyway, you take the first half of the weights from Craig, from DeepDrive, and you load that into this weight matrix here. And then you do similarly for the biases, and then the other half. And again, you have to transpose you just have to transpose the axes, because where the shapes likes to be. Recap on what we're doing this session. We're just sort of reviewing things I did this weekend related to the self-driving car model. So right now we're looking at the transfer model and how to get the weights to line up. In a little bit we'll look at the actual transfer model that I tried to, well, we looked at SqueezeNet. Now we're looking at trying to use the DeepDrive model and see how that works. I just wanted to see how it did. Craig was having trouble getting it working outside of Cafe properly. The model was always always predicting shift left, which I was seeing a little bit of that in my own models. So I was curious if I could get this running. Anyway, you can assign the rest of the layers, pretty straightforward. And then I saved them. I saved those layers as a one file, so I don't have to do this every time. And then you can just load them up. So it takes a little bit, because AlexNet is like 227 megabytes or something like that of parameters. All right, where am I? I'm over here. Okay. And the other thing, it's you might recall in one of the earlier videos, I eventually figured out that the images are in blue, green, red rather than red, green, blue. So I need to like switch those back. So they have, and that's just the way AlexNet in the Cafe setup is. Oh, that didn't work at all. That did not work at all. That's where I am. ... / really? Do I just not have that anymore? Really? Images array, images. Oh, I got rid of that. Right. I'm a terrible person. I am a terrible person because I added more data, is the other thing I did. Let's just not even. We'll get to that in a second, though. And I, of course, managed to nuke my old data set. Someone also asked from a lot of questions from the audience. I like this today. That's good, because I didn't have a lot planned today, so that's perfect. Currently using Theano backend on Windows with GPU. Would I gain significant speed advantages in training/inferring if I switch to Linux and run the TensorFlow backend? That is a good question. I don't know inherently that you would. Personally, I strongly prefer to develop in Linux anyway because I have much more control over my environment. I can set up an environment like this where I've got the whole screen, and I can very explicitly control everything about the program that I'm running. I don't know. My base inclination would be that you would probably see some speed up, but I don't think it's going to be an order of magnitude speed up. I don't know, maybe 10%, maybe less. It depends on how the drivers are configured, if the libraries all work well. I would say work wherever it's most convenient for you to work, and then when you need to spend 2 weeks training a model, that's when you get a serious beefy computer that can just run for a long time and you let it go. And I have a feeling that's probably going to be running Linux, just the way that goes. Alright, what did I do here? I was just grabbing 100 chunks of data and upscaling them, because my data was only 64 by 64. I shrunk it down. So I said, alright, well, let's put it back, right? If I say plot.imageShow upscaled 0, is that going to work? Nope, that's not going to work. Transpose. Let's see. I need to put what's in the beginning in the end. So it needs to be 1, 2, 0. Right? One more. Yeah, there we go. Well, and the red and the green, those are also mixed up, of course. Let's see. If the channels are first. Let's see if I can show an actual image here. Almost. Almost. Not quite. Yeah, there's something else flip-flopped around. Alright, but those are the images. Actually, I wonder if that's totally what's screwing me up. No. Unless it's like is it a 1 minus thing? You know, I'm not going to spend the whole episode thinking about that. That is not gonna... That's going to drive me insane. Trying to think, oh, is this picture not quite exactly what it's supposed to... Oh, I'm going to go crazy. That's not the purpose. So you can just generate the predictions for that model. And I believe... So Craig's model, it outputs... 6 numbers. And I thought this last number was the steering, perhaps? I need to look at his README on this, though. So he's got his data set on Google. You can check it out. He's got a README, which he does update. It's very good. If we get really bored, I have a couple other things to show. So here he says number 4. That's a speed change. The throttle, the last one, is steering, he says. Yes. That makes sense. And you'll notice, you see a lot of 0.2s here. So let's plot those. Oop, there we go. Steer preds. Grab the steering predictions. And you'll notice these are the actual predictions. Also, this model goes -1 to 1 as far as the steering. And I believe... Did I actually account for that somewhere? Oh, well, I'm just comparing to the targets. So I'm not doing any training on this model, so that's fine. And yeah, that's right here. I'm saying, hey, rescale this 0 to 1 to be -1 to 1. And you see, like, it's just pretty much listing. Listing left, I believe, is how this works, because the steering is a little backwards, I think. I get easily confused by this anyway. Another question from the audience. Do I plan on using data released by Udacity? I still haven't had a chance to take a look at that. Someone mentioned it to me, I think, in the channel or on Twitter or in a comment, or someone even emailed me. I just have not taken a look at that yet. So for those who are wondering, if I search Udacity, self-driving car, it should come up pretty quick. They put out a challenge, and they have their own like nano degree, and they want an open source self-driving car. That's what it was. Yeah. And they had released self-driving car Android dashboard using deep learning to predict steering angles. Yes. That was exactly the problem. This is exactly what we're trying to do. Hey, what do you know? So, where they had the freaking data listed somewhere. This is like the special announcement. I just wanted to see, like, where's the data? Show me the data. Scoring, evaluation metric. How do I get started? Download the data sets here. Yes, but of course the data sets are... So they have a GitHub page, Udacity/self-driving car. And the data set is 40 gigs, or 25 gigs you want to download, 40 gigs uncompressed, and 124 gigs. So again, for just consumer purposes of fooling around and like learning how to do what I'm doing, that's not the kind of thing I want to casually just download and futz with. But I probably will look at this at some point and see if that's a little better. Images? Nah. Oh well. But yeah, this would be kind of a cool challenge to try, and I guess that'd be something I should just, since I'm doing this anyway, I might as well try this challenge. It would be fun to have a model that already works on something else and just submit it blindly to this. And just say, like, make sure it reformats and runs and does something, and then just see how it works on their data. That would be an interesting thing to do. All right, so I didn't have a lot of success with Craig's model when I was able to read in the weights, but I was able to read in the weights, and it does something. So that's, in theory, you could do some transfer learning with that as well. So we covered the transfer learning with SqueezeNet, and that didn't work out so well. Like it worked, it ran, it did stuff, but it wasn't giving me very good results. And I was trying this AlexNet thing from DeepDrive, and I was having a hard time with that too. And I was like, ugh, well, no, I'm never gonna get a model to go anywhere. Blah. Why do I like forget it? I'll write an heuristic to. I'll just do it this heuristically. I'll throw machine learning out the window. And then I remembered I saw an interesting post. Self-driving RC car. Let's see where that is. No, this was very recent. It was on GitHub. Maybe I can't find it anymore. There was also NVIDIA. Alright, it was based on this. So NVIDIA has released at least a model of one of their self-driving car things. So I thought, alright, well, let me take a look at that and see how they do it. Driving data model, there we go. And so this gives you just a sense of what kind of model they're using. So they're using TensorFlow. I consider that kind of irrelevant. Use whatever library works well for you, whatever you have available. And they're just doing some pretty standard things that don't look crazy. I mean, this is just several convolutional layers, like 5 convolutional layers of some like reasonable number of kernels, of like 24, 36, 48, 64, 64. Like those aren't huge numbers. And then a couple fully connected layers of 1164, it looks like. A couple dropouts, then 100 nodes, then 50 nodes, and then 10 nodes. It's narrows down quite a bit here. And then finally, they're using tanh to scale the output, I believe. So again, they're trying to compute between -1 and 1. You know, I saw the video of their model, and that seemed to work pretty dang well. I was impressed with that. I like that it navigated construction, and so I thought, okay, maybe I was being too timid in what kind of model I was willing to do. Race car on Jetson Hacks channel. I may have to check that out. Rick has an interesting link in the chat for anyone in chat. Otherwise, check out Race Car on Jetson Hacks. Okay. So I said maybe we can do something similar. I did think making the exact same model, and that was just too big for my computer to reliably get through in an acceptable amount of time. So I said, okay, let's try a similar model, and in Keras, of course, because that's where I like to operate. That's where I'm most comfortable. And I think I'm still using ELUs, apparently. I wasn't using real U's. Apparently not. Definitely thought I was. Alright, that's fine. So I said, okay, let's just do 5 convolutional layers, sort of like they have, of comparable, but generally reduced numbers of kernels. So I started 24, and I said, alright, let's just increase by like 8 each time. Except for some reason I did not hear. Oh my goodness. I got a bug here. And I trained this model for a while. That's embarrassing. That's real embarrassing. I'm going to have to redo that. That's otherwise is it like I only have 4 layers. Another question from the audience. What kind of GPU do I use? NVIDIA GT620. Just check the, I don't know, like 30 minutes back in the video. You'll see I mention it. I really just need to put that like on my webpage somewhere. I use this hardware. It's terrible. I know. Oh my gosh, this is super embarrassing. I did not update all of these. That's super embarrassing. I'm gonna have to like retrain this model down, see if it still works. If it doesn't, then I just go back to 4 layers, and I declare that to be victory. Let's do this. I like that. I like that. That's pretty good. So that's now pool L4, drop L3. Yeah. So we got the standard stuff: dropout percentage, I'm still using the exponential linear unit. I was having much better success with that, so I'd like to continue using that. Oh my gosh, that's just misery. Right, and then I added a few more layers on the output side. So I have just fully dense connected layers of 256, 128, 128, and then 64. And then finally the single, ignore all this stuff. Let me just make sure to make this go away. That's old. That doesn't exist. That's gone. And then the final linear layer, of course. And that's all. This all should be good. 1, 2, 3. Yeah, okay, that's good. Whew. This could be misery though. So yes, 5 convolutional layers, and then 4 densely connected layers, and then you get into your simple model. And you might notice, got a slightly different data files here. So I thought, maybe the 18,000 or so frames that I have, maybe that's not enough. Maybe I just need more data. So I went and downloaded another 20 or so files from DeepDrive, and I just incremented. I said, all right, I had like 1 to 10 and like 470 through 490 for whatever weird reason. And I wanted to make sure to grab these. Problem was, I'm reading these in, and I have marked which frames are bad, but I marked that with an overall count over here rather than like within each file. So if I'm reading these in and I happen to read these files, these new files, before some of my bad files, my count gets all off. So I said, forget it, I'm just going to rename all these files so that they must come after these. I'm not doing anything with recurrent nets or using the relationship between frames, so that's not going to hurt me. That's not a big deal. And I scanned through these new files, and I didn't see any really bad situations. So it should be okay. Otherwise, this is the same script I have for shrinking the data set. So again, reading in the, I think, 227 by 227 image, scaling down to 64 by 64, scaling the speed, throttle, acceleration, steering, all that jazz. And then saving it off. And this should be big too. So I have that. And now I should really rerun this model and see what happens. It's gonna take, it takes like 5 minutes to get through an epic though, because there's a lot more data, and this model is actually pretty large. So let's see what happens. Get through 5 convolutional layers. Flatten those bad boys. I still cannot believe I forgot to just add like a typos in the model when that layer was basically not getting used. I mean, it was basically just a 4-layer model then, so it's going to take longer to run even now. Maybe, although there'll be fewer parameters, since there'll be additional pooling. So this is one downside of using a tool like Keras, where it's easy, the model could still run even when you've got some typo like that. It's just not doing what you would have expected. Oh, I didn't like that. Oh, right. Whoop. Hang on. Yeah, I hear you, buddy. I hear you. Where are we? Let's get out of there. Give me that. Yeah, it takes time just to read in the data now. Oh, misery. So we say 100 epics. I found letting it train for more than, I don't know, 20 was not helpful, actually. Like the model, I might have had a bad learning rate, but it did weird things. The loss just kept, it was growing to an insane amount. It was in the, I don't know, billions or trillions when I checked it like in the morning after training all night. So yeah, the learning rate did some bad things to the model. And that was, it maybe got, 40 passes on the data, maybe 60. So this, you'll notice, 500 seconds. So a little under 10 minutes to train, which is longer, which is frustrating. I guess I have more convolutional kernels. What's the benefit of the Atom optimizer? So Atom is an alternative optimizer to SGD, stochastic gradient descent. Stochastic gradient descent, let's just start there. That is an optimizer where you compute the gradient, what is the direction that you should nudge your parameters, and you move in that direction a certain amount. That's plain gradient descent. Stochastic gradient descent says rather than like computing it over all your data and then moving the whole way, compute it over like one point or a small batch, say, and then move in that direction of that batch, and then read the next batch, move in that direction. So you're kind of moving around a little bit. And the learning rate controls, if I'm supposed to move in that direction, how much do I move relative to whatever the error is. That's the idea. Atom, I am not 100% familiar with. Atom Optimizer. I believe it has built into it sort of things that I'm gonna mix this up. I'm very likely gonna mix this up. Here, maybe this thing will clarify. 2 data science experts. Basic intuition between atom. 10 minutes for 100 epochs. Oh, no. That's 10 minutes for 1 epoch. If it was 10 minutes for 100 epochs, that would actually be fine. Because then I would just do 10 epochs and let it take a minute. You'll notice I've got 32,000 data points, whereas before I had like 17,000. So we about double the amount of data we had. So you could cut your training time by taking out data. That's always a viable solution, and then it will only take 5 minutes. Of course, then you look at less data. Alright, so we talked about gradient descent. This guy's talking about that, yada yada yada. Can I, in 30 seconds, figure out how to explain the atom optimizer? That is the question. And the answer is no, because this guy's not explaining it. Alright, so I don't have a good answer for how the atom optimizer properly works. First order gradient-based optimization based on adaptive methods. Right, so I think it's essentially fiddling with the learning rate as you go based on information from previous iterations. I believe that's the idea. So you can sort of know when, oh, I can afford to jack up the learning rate and move a little more versus I need to be very careful and move very slowly in this situation. I believe that's the idea. And you can tune parameters to sort of get that exactly where you want. But part of what they say here in this canonical paper is that typically requires very little tuning. So that's considered an advantage. But that only killed like 3 minutes. So the loss here is the mean squared error, of course. So if we're typically off on our model by like 0.02, that means that our means if we're typically off on the model by like 0.5, say you're half wrong based on which direction you want to go because we're from 0 to 1, then that implies that your mean squared error would look like 0.25, right? Because you square that number. So if you're off by like 0.2, your mean squared error would be about 0.04. And you might recall in previous models we had gotten down to the point of like 0.03, and with using Isaac's model he had gotten down to like 0.02. When I fiddled with this model, that had a typo apparently, but it was made the model smaller, so now we're bigger. We should be fine. Worst case scenario, I just go back to that model. And I stopped using this, whatever I used the model that was a typo. If that turns out being better, then that's perfect. That's great. It got down to less than 0.01. Now, granted, part of that is that we have more data, and that data might be more well behaved, and so getting a good model might be a little easier. But I did honestly look at the data, and it did do a decent job. And I still have 3 minutes to kill. Oh my goodness, this is murder. So that's sort of the current state of the self-driving car model situation. While this is still training, I want to like briefly look at another problem. Not neural slime volleyball. That is a cool project though. I just saw today. Because I'm not the only person working on this project. There's also this Arduino folder. So this is how the model actually talks to the car. And I want to make sure we see. I haven't actually looked at any of this code, and hopefully Rick Rick, hopefully Rick's not paying attention right now as I scroll through his code and wonder what's going on. But we had some funkiness as for hard. We're talking over the byte, not the byte, oh gosh, the serial port, or at least a fake serial port over USB. And we're getting weird things there. Check if auto on, yeah. So I wanted to see, do auto commands. Rick does say that he's here. Of course, I'm like committing like the horrible sin of like not just trying to learn something while streaming, but like trying to read code while streaming. At least I'm vaguely familiar with Arduino code and C in general, and I have seen that. I've like looked at this once before over my shoulder. Right, we had to flush the read buffer. That was one of the problems. The Arduino was not reading from the serial port if it wasn't in autonomous mode, and so the buffer would just fill up, and then the model would think that it's broken because it's trying to shove things down the serial port and it can't put anything there. So that was an amusement. So it worked when it was in autonomous mode, but it did not work when it was in debug mode. That's like a classic Heisenberg bug. But we're still, I feel like I remember there was times when the model was definitely saying go left, but the car was not going left, and we had it in autonomous mode. So I'm not sure what the challenge there was. There might be just some issues with the steering, getting it to communicate. I know Rick was going to look into steering just using the back wheels. So I was trying to think about this the other day, how you look at the left wheel and the right wheel, and you know that you want your turning angle to be a certain amount, and if you sort of draw the lines that the arcs the two wheels have to follow, that gives you two different curvatures, and you can use that to relate what the speed should be of each one, given that you're going at a certain like average speed in the middle. I thought about it a little bit, and like I feel like I had a brief moment of clarity and understood it, and then it was gone, flash, and it was no more. Like I'd have to sit down on paper and work that out again. And I'm sure this has been worked out by people already, but it's always helpful to understand what you were looking at yourself. All right, this is not quite what I wanted. Oh, well, there we got 0.17 something. That's something. Yeah, so validation loss, 0.009, which I found interesting. And like even the mean squared error on the actual model right now, not half bad. Not half bad. All right, I'm gonna interrupt this actually. I want to have a brief look at whether this model is at right now. Just a brief look. Let's see if we're actually predicting something. Left turn, make right wheel go faster. Right turn makes the left wheel go faster. Yeah. The question is how much exactly, and when you're going different speeds, I have to think about like, does the ratio change? Because it's a matter of whatever the curvature is. So you know the right one needs to be going faster, and that'll send you along a particular curve. Alright, but I want to just look at the data now. Look at the results. After 1.01 epochs of training. Show me the results. Come on. So everything takes longer when there's more data. This is, again, like a cardinal sin of streaming. I'm just sitting waiting on the computer. And for this, there's not a lot to do. I'm literally computing everything. Sending every data point through. So that just takes a certain amount of time. I did not think it took this long. But then again, everything takes longer when you're watching it. Oh my goodness. This is awful. Awful. Oh, come on. I did have another plan. I wanted to make a model that was purely linear. I had, when I first started this plan to just make a model like that, just to see how things go. You know, it's a reasonable place to start. But for some reason, never got around to it. Or I had a model, and then I still did some convolutions for whatever dumb reason, which I should not have done. Another question from the audience. You haven't checked in the past streams, but will you be pulling together several networks for a final model? I probably will not be doing that, in all honesty. That is a thing you can do. It's called ensemble models. And so you sort of have several different models, you run them all, and then they sort of, this one works more in certain situations, this other one works in other certain situations. You can sort of take an average, or you can have sort of a foreman model that tells you which one of these you should use, is one strategy. I don't think I'll be doing that though, because that just means I have to train and manage that many more models. And I really don't want to do that. It already takes too long to get the models that I have now working correctly. So I want to make, right, while I'm waiting for these damn predictions to finish, that's taking forever. I guess part of it is that literally I'm streaming, I'm encoding video and sending it to YouTube all the time. That is probably what's slowing me down. I would not be surprised if that were the case. That would make, in fact, a lot of sense. Let me grab this stuff. So we are making a purely linear model. Whoop, that's not what I want. There we go. Let me grab this one. Here we go. That's what I want. And you work on M. There we go. How do I handle overfitting? So far, that hasn't been a super big problem because I just don't have that much data. But I have implemented some, in whatever the most recent model was, I did have some dropout layers and some regularization. A very, very lightweight regularization, you'll notice. 0.01. And we have some dropout training where, for a particular layer, when you are training, you say throw out, X% of the data. Just throw out X% of those nodes and call them 0. And so that you don't fit too explicitly. No one node is gonna become too fixed on one thing. That's the idea anyway. All right, let's see how one epic did here. All right, that's not really what I want to see. So the green is the target, the blue is the actual. And you see, well, this was only after one epic, so it might be crazy. But it's just not varying that much. It's always between 0.4 and 0.5. And really, I want it to be fixed on 0.5. You notice I'm off by about 0.05. Why? I don't know. So that model might need a little more time training. It might mean that I need to go back to the 4-layer model. Maybe that was better. I want to very quickly, however, train a linear model, even with a ton of data. I want to see what happens. I think it might be very interesting. So this is real in, that just takes M, flat, yeah, this should be good. Let's do that. So if we say model.summary, you can take a look at what's going on. And yeah, there's about 12,000 data points, most of which is going to be 64 times 3. Yes, the vast majority of which are the pixels in the image. And then there's 3 more. No, there's 2 more plus bias term. That's all. That is it. And so this is a purely straight up linear model. And this is often a good place to start. So we are going to do that. I want to see what happens here when I do this. How fast does it run? It should be, yeah, way faster, first of all. We can blitz through the data in, 10 seconds. So you can actually train for a while. Of course, with linear model, I feel like you definitely shouldn't need as much training because it is purely linear. You could, in theory, just snap your fingers, do the normal equation, and get an answer. And in fact, that might be a more sensible thing to do, as I see this is doing some strange things. This loss should just be going strictly down. But there's various points in the model. The validation loss is what I care about here. But it's still terrible. Why is it so terrible? So for a real linear model, yeah, you would snap your fingers, do linear algebra, and get the right thing to do what you want. That is horrendous. That is awful. Do I have sklearn here? Hang on. Import sklearn. Sklearn.linear. Nothing. Ugh. from sklearn import. Can I do that? There we go. Not metrics, models. Multi-class, naive Bayes, natives, linear model. There we go. Linear model. There we go. Linear model dot fit. Can I do that? What are the options? Like, I don't remember how to use freaking sklearn linear models. That's just classic machine learning type stuff. Oh, this is the class of linear-based models. Linear regression. Hey, what do you know? Fit intercept. Yes, normalize false, copy x true, and jobs 1. Oh, cool. If -1, all CPUs used. Huh, cool. And you spit out, oh, those are the attributes. So, you say L equals linear model dot linear regression. Import, no. From sklearn, import linear model. There we go. So sklearn, for those who don't know, is a general, you might call it machine learning modeling framework with a lot of the classic methods, such as linear regression, support vector machines, logistic regression, all that kind of stuff. But I don't believe it has neural networks, and it doesn't use the GPU or anything like that. It just tries to be very classic. I should be able to just say whatever L.fit. Yeah, there we go. L.fit. And it should work the same way. So these are my inputs. Boop, boop, ba-doo. And these are my outputs. NumPy array of shape, n samples, n targets. Which this targets 0. Now I'm going to get burned here because I need to add on, I need to reshape images and speeds. I need both of those things together. So the question is images.shape. And so if I said images.reshape, and it's going to be -1, comma 3 times 64 times 64 dot shape. Yeah, that's right. And I want numpy.concatenate, smash those things together. So we'll smash this together with speed x. We'll say axis equals 1. Can I get away with this? One more. Put those into a tuple. I should have. And x.shape. Is that the right shape? It is. Look at that. Look at that. Incredible. So let's just stuff that in. So all I had to do was flatten the images ahead of time, sort of. Whereas in the Keras model, I could do that inside Keras using this flatten routine. Yeah. So that shouldn't take forever. Also, it helps it when I, finish the... There we go. Wait, what's going on? There we go. No. Nope, 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 nope. Did not finish what I was started. I wanted this whole thing. There we go.